now we are ready for L'Hopital's rule, section 4.4, which is about indeterminate forms. And it's a new rule that helps us figure out the limit of indeterminate forms. And so before we jump into this, let's recall something that we have seen before, an indeterminate form that we've seen before. Suppose we're asked to find the limit as x approaches 3 of x squared minus 9 over x minus 3. If we were to plug in 3, use direct substitution, which is always what you try at first, so we would get 3 squared, which is 9, minus 9 over 3 minus 3, or a 0 over 0. And so indeterminate means we can't determine the limit at this point, so we need to try something else. And so what we would do is, what we did was say, well, maybe we can factor this. So maybe we can factor this. And so if we did, we'd say, well, this would be equal to the limit as x approaches 3 of x plus 3 times x minus 3 over x minus 3, because this is difference of squares. And when we did that, that was helpful. Then those two factors cancel. And we get the limit as x approaches 3 of x plus 3. Then we can use direct substitution, and we're not dividing by 0. We don't have an indeterminate form, and we get a nice little limit 6 right there. Okay, so what we can handle indeterminate forms of this nature sometimes if we found that it could factor. Sometimes we would multiply by a conjugate to help it determine the limit. Sometimes we would find a common denominator depending on the situation. So let us see what this L'Hopital's rule says. It says that if you have, on your sheet it's written out a little bit better. I just did like the gist of it here. It says, suppose you have some function f and g and they're differentiable, and that g prime of x doesn't equal 0, and on some open interval I that contains a. If we have an indeterminate form of the type 0 over 0 or infinity over infinity, then the limit as x approaches a of this indeterminate form, 0 over 0 or infinity over infinity, is equivalent to the limit as x goes to a of the derivative of the numerator over the derivative of the denominator. This is a very powerful rule, and if you look in your textbook, they give a proof of this, and you should look at it and see why we can say this is true. Please take note that this is not the quotient rule for a derivative. This is not low d high minus high d low over low low. That's not what this is. This is just straight the derivative of the numerator over the derivative of the denominator. And these are the conditions when we can apply L'Hopital's rule. So let us apply it to this one. We already said, what if we wanted to find the limit of this, which we already know how to do by one method. What if we wanted to try L'Hopital's rule for this? Then how would we approach it? Well, they say, okay, find this limit. That's what they said to do. Find this limit. What we would do is say, well, let's use direct substitution, and once we use it, we say, oh, we have 0 over 0. That gives us the license to use L'Hopital's rule. So that means we come in here and say, okay, let's do it then by L'Hopital's rule. Then this limit is equivalent to the limit as x approaches 3 of the derivative of the numerator, which is just going to be 2x, over the derivative of the denominator, which is going to be 1. And then we can use direct substitution and say this is just going to be 2 times 3, and we get 6, just like that. So now we have another way that we can find the limit of this indeterminate form. This is a very powerful rule, and we're going to see different ways that we can apply it in this section. So let's jump down to your first example. And so it says the limit as x approaches 1/2. The limit, oh, I made it capital L. The limit as x approaches 1/2 of 6x squared plus 5x minus 4 over 4x squared plus 16x minus 9. Okay, we have to take this limit. So what we know how to do is try direct substitution. So if we use direct substitution, what we get is, what did I get here? I got 6 times 1/4 plus 5 times 1/2 minus 4 over 4 times 1/4 plus 16 plus 8 minus 9. And when you plug this in, you get 3 halves plus 5 halves, which is 8 halves, which is 4 minus 4 over 1 plus 8 minus 9. And 4 minus 4 is 0, and 9 minus 9 is 0. So we did this this is an indeterminate form. We are allowed to use L'Hopital's rule. So now we're going to apply L'Hopital's rule. Okay, so by L'Hopital's rule, this limit, okay, is equal to the limit as x goes to 1/2 of the derivative of the numerator, which is 12x plus 5, over the derivative of the denominator, 8x plus 16. And then we can use direct substitution and see what happens. When we plug in 1/2, we get 6 plus 5 over 4 plus 16, and we find that this limit is 11 over 20 by L'Hopital's rule. So that's kind of nifty. Let's look at number 2. Number 2 says let's find the limit as x approaches pi over 2 from the right of the cosine of x over 1 minus the sine of x. So let's just take note of this one. I'm about to apply this to a one-sided limit. There's a theorem, and if you look in your text, you can see where it's written out, that says L'Hopital's rules can also be applied to one-sided limits. So if you're approaching something from the right or the left, you can still use this rule if these conditions are met. You're looking at an indeterminate form of 0 over 0 or infinity over infinity. So you must always check to make sure that those conditions are met. So let's use direct substitution. So right here, the limit as x goes to pi over 2 from the right of the cosine of x over 1 minus the sine of x. Recall the unit circle. So here's our unit circle. All right, so this is 0, this is pi over 2, and this is 3 pi over 2. The cosine of x, when it's at pi over 2, is the x value. So this is the 0.01. And so the cosine is the x value, which is 0. So we're looking at a 0 in the numerator, over 1 minus the sine of pi over 2. The sine is the y value, 1 over 1. So this is a 0 over 0. We're looking at an indeterminate form of 0, 0. So we can use L'Hopital's rule. So let's apply L'Hopital's rule. It goes like this. So this is equal to the limit as x approaches pi over 2 from the right of the derivative of cosine, which is negative sine of x, over the derivative of the denominator. Derivative of 1, which is a constant, is 0. This negative 1 is a constant that just gets multiplied by the derivative of sine, so this is going to be negative cosine when we take that derivative. Okay, a negative over a negative is a positive. Let's use direct substitution, see what happens. So if we put in pi over 2 to the sine of x, what happens? Sine of pi over 2 is 1. We get a 1. Okay. We put in pi over 2 into the cosine of x, it's going to be 0, but it's not quite 0 because it's a one-sided limit, so it's something very close to 0. So very close to 0. This is a little bit tricky because it's an angle, right? So positive angles move this way. So if this is a little bit to the right of pi over 2, that means that we're a little bit on this side, a little bit positive on this side of the y-axis. So we're on this side of the y-axis, then the cosine is negative because we're in quadrant 2. So over here, the cosine is negative over here. So we're looking at a little tiny negative number. So 1 divided by a very tiny negative number pushes us to an infinity, and negative infinity is going to be what that limit approaches. So you got to remember how when you're dividing by something real tiny. We did that earlier in this course. That's what's going to happen there. All right, let's do example number 3. And it says this: find the limit as x goes to, what does it say? 0 from the right. Okay, it's another one-sided limit. The limit as x goes to 0 from the right, and now we have a logarithm. Okay, that's no problem. Of x over x. Okay, so number 3. Number 3, the limit as x approaches 0 from the right of the natural log of x over x. Okay, what's going to happen here? The natural log, the limit as x goes to 0 from the right of the natural log of x. If you recall what a logarithmic graph looks like, it has a vertical asymptote here. And you can only put in something positive into a logarithmic graph. And so it hugs the y-axis here and then it approaches. This is what the natural log of x, the graph looks like. So, if we're trying to find the limit of the natural log of x as it approaches 0 from the right, we are way down here at negative infinity. We're looking at a negative infinity. All right, if we put in 0 for x, we've got a 0. So this is not one of those. So I cannot use L'Hopital's rule here. This does not meet the conditions. However, I can determine the limit. If I have any number being divided by something very tiny and positive, so this isn't quite 0. This is really a tiny, close to 0, positive. Okay, just like in the last example, when we had, what did we have there? We had like 1. Yeah, it was 1 divided by something tiny and negative. This pushes this to an infinity, and that pushed it to, because this was negative, it pushed it to a negative infinity. Well, if we've got something divided by a tiny positive, this is going to push this to an infinity. And if it's already going to infinity, it's going to push it further to infinity. So our limit's going to go to infinity. The fact that we have a negative divided by a positive means negative infinity. What happened here is we did not even need L'Hopital's rule to use this. We could determine the limits by using other methods. Plus, we were not even allowed to use L'Hopital's rule here. What if, though, you're on automatic and you're like, oh, I know I'm in section 4.4, and we're learning this rule, and it's kind of fun to use, and it's real easy to use. Let's just do that. What would we get? Well, let's just do that. What if we just applied L'Hopital's without thinking? We said this is equal to the limit, and so this is wrong, by the way. What I'm about to do is wrong, but let's just suppose you were not paying attention, and you just said, okay, let's just go for it. Well, this is derivative of natural log of x is 1 over x. Derivative of x is 1, so we get, this is 1 over x, this is equal to the limit as x goes to 0. And so if you did that, you would get positive infinity, but that is the wrong answer, and all of this is not even supposed to happen. So just be careful, because if you're not, don't do the test first and see whether or not you can use it, and you just use it without doing the test, you get wrong answers. So just pay attention to that. All right, let's look at the next thing. What if we come across the scenario where we don't have this indeterminate form? Sometimes you can manipulate legally, mathematically, through what's okay to use the form that you are given to make it be a 0 over 0 or an infinity over infinity. And then you can apply L'Hopital's rule. So it becomes pretty powerful rule to use because you can apply it in a lot more settings. So let's look at example 4, and what we have here is this. The limit as x approaches 0 of the sine of 5x times the cosecant of 3x. And so if we just use direct substitution, let's see what we get. Remember your unit circle. Okay. If 0 goes in for x, we have 5 times 0, which is 0. So the sine of 0 is right here, and the sine of 0 is a 0. We're looking at 0. The cosecant is 1 over sine, and so the cosecant of 0, 1 over 0 is infinity. So we're looking at an indeterminate type of 0 times infinity. So there are other types of indeterminate forms that we come across, and so this is one of them. Let me just show you some of the things we'll be seeing. You can have a 0 times infinity is an indeterminate form We don't know. There's a struggle between the f function and the g function. If this is f of x and this is g of x, let's say, there's a struggle. We don't know if 0 is going to win or if infinity is going to win here. Also, if we have this another indeterminate form, infinity minus infinity. Here's a f function, here's a g function. We don't know if f's going to win or g's going to win when we're finding this limit. It's a struggle. We don't know. In a minute or on the next video, we're going to look at powers. Here's other indeterminate forms you can have. They're the power if you have 0 to the 0, infinity to the 0 power, or 1 to the infinity. These are all indeterminate forms. There's a struggle between the f and the g function. We don't really know who's going to win out, who's going to be more powerful in these scenarios. So we have to do a little work to look in to see what the limit's going to be. So we're going to see these in a few minutes. Right now we're looking at a product. So since we can't really determine what the limit is in this shape, is it possible we could use L'Hopital's rule? It is possible if we can rewrite what we're given into this quotient. So we have this quotient division, 0 over 0 or infinity over infinity. Can we manipulate this algebraically to make it be one of these forms? And with a product, it's pretty easy to do. Let's do this. What is cosecant? Cosecant, in general, the cosecant of some angle, right, is equal to 1 over the sine of that angle. Let's rewrite this into the limit as x goes to 0 of the sine of 5x times 1 over the sine of 3x. That is okay. Then let's talk about this like this. The limit as x is 0 of the sine of 5x, see, we can multiply these fractions together, over the sine of 3x. What does that give us? Well, the sine of 0 is 0. The sine of 0 is 0. Oh, this is the indeterminate form 0 over 0. Now we can apply L'Hopital's rule. So let's do it now. Let's apply L'Hopital's rule, and let's see what happens. This is equal to the limit as x goes to 0 of the derivative of the numerator. All right, derivative of sine is cosine, and this has a little bit of chain rule, times the derivative of what's inside, 5, over the derivative of the denominator. Derivative of sine is cosine. This has chain rule, times the derivative of the angle, 3. And let's see what happens. The cosine of 0 right here is 1. So that is going to be 5 times 1. The cosine of 3 times 0 is the cosine of 0, which is 1 times the 3. And this is going to be the limit of this indeterminate form. So we took this product and we rewrote it into a quotient. All right, let's look at the next example. It is the limit as x goes to infinity of x times the sine of pi over x. The limit as x goes to infinity of x times the sine of pi over x. Okay. Let's use direct substitution. Infinity goes in for x, infinity. The sine of pi over infinity. Pi over something, a number over infinity is basically a 0. So the sine of 0 is 0. We're looking at this indeterminate form. It's a product. I would love to get to use L'Hopital's rules, but I can't right now because this is not the quotient. Can I rewrite this into a quotient? And I can, and you can too. And this is what I'm going to do. I'm going to rewrite this into the limit as x approaches infinity of the sine of pi over x over 1 over x, which is equivalent. Let me show you how I made this look like this so that it doesn't, so you can know how to do it too. All I did, and you're allowed to do this too, is this is over 1, right? So I said, let me multiply this by 1 over x over 1 over x. And this is a 1, so that's legal. So basically x times 1 over x became a 1 times the sine of pi over x. And 1 times 1 over x is this. This is why this is legal. Now, if I use direct substitution again, the sine of pi over infinity is the sine of 0 is a 0. 1 over infinity is a 0. And now I see that I've got this indeterminate form. So I'm allowed to apply L'Hopital's rule. Okay, so once we do that, I've got this indeterminate form. So this is equivalent to the limit as x approaches infinity of the derivative of this. Okay, derivative of sine is cosine of the angle times the derivative of the inside. Okay, all right, let's see. What's the inside? This is just me thinking. This is pi over x, or pi times x to the negative 1. I'm going to think of it like this. The derivative of the inside is power rule. Negative times, this is going to be times, negative pi x to the negative 2. That's what just happened there. All right, over the derivative of the denominator, which is 1 over x. Okay, 1 over x, let's think about that. 1 over x is x to the negative 1. The derivative of this is going to be negative x to the negative 2. So this is what I have to evaluate. I see where I can do a little bit of a cancellation here, common factors. X to the negative 2 can divide into x to the negative 2 one time. This negative can go into a negative, become a positive. So what I'm looking at basically is the limit as x goes to infinity of pi times the cosine of pi over x over 1. So basically this is all I'm looking at. If infinity goes in for x, pi divided by infinity is basically 0. The cosine of 0 is 1. So this is really pi times 1, or pi is what the limit is here. And you wouldn't know that looking at this, but we were able to figure that out through some algebra and applying L'Hopital's rule. So in the next video, we'll look at what we do when we have to have infinity minus infinity, and then the power indeterminate forms.